Okay, welcome back. This is 10.3. We're going to now multiply and simplify rational expressions. Oh, sorry, radical expressions. Okay, so adjust this thing. So first off, we are introduced to the product rule. So if you have some radical and you have a product inside the radical, you can take that and tear it apart and have two radicals. Okay, so a radical for A and then times a radical for B. And vice versa. You can also go the other way. So if you started over here, you could also go that way. So it's kind of a double way. Okay. Okay. So why am I allowed to do this? Well, if you turn everything into exponents, you kind of see the workings, the goings-ons. So let's start on this side over here with the square root of A times the square root of B and see how it works with exponents, right? So the square root of A, we can always write it as A to the 1/2. And then the square root of B, we can always write as B to the 1/2. Okay? And then we could use the product to power rule to rewrite it as A times B to the 1/2. And then clearly, or hope it's clear, you can replace the 1/2 with a square root symbol, and you just have the other side. Okay. So we could apply this then. We're eventually going to apply it to simplifying, but let's just look at some of the intro exercises from the book. So we have the square root of 7 times the square root of 5. Sorry. So I want to rewrite it as one radical. So it's the square root of 7 times 5, which is the square root of 35. Okay, let's look at number 6. We have the cube root, or the fifth root of 9 times the fifth root of 3. So as long as you're dealing with the same kind of root, this rule always applies. So I mean, you could kind of slip any root power you want in there and it'll still work. So in this case, we can rewrite it as the fifth root of 27. Let's look at 14. We have the sixth root of x minus 5 times the sixth root of x minus 5 to the fourth power. Okay. So as usual, I can just multiply them out. I get the sixth root of x minus 5 to the, well, this is the first power, and then if I multiply it by this, you just add the exponents. Okay, so if they have like bases, you add the exponents, and you end up with x minus 5 to the fifth. All right, let's look at 20. So we have some more variables to deal with now. It's the ninth root of 12x squared y cubed times the ninth root of 3x cubed y to the fourth. Okay. So to rewrite it as one radical, you just multiply everything out. Remember, if you have like bases, you're going to add the exponents. 12 times 3 is 36. X to the squared times x to the third. You add the exponents for x to the fifth. And then y to the third times y to the fourth is y to the seventh. Okay. Okay. So we want to learn how to simplify these things. And hold on one second. Sorry. Yeah, we want to simplify radicals, and the way I do it, I think of as kind of marching the perfect squares out the front door. Okay, so you're going to factor the expression you're given into perfect squares, hopefully, or at least factor out the perfect squares and then march them out of the radical. Okay, so how does that work? You're going to use the product rule, and you need the product rule in order to do this. Okay, so let's take a look here. Number 22. We have the square root of 27. Okay, so this will take a bit of experience dealing with perfect squares. Like, you have to be able to kind of have them in your brain somewhere in order to factor this, right? So a perfect square that divides 27. You're thinking 4, no, and then the next perfect square is 9, so yes. So this is the same as 9 times 3. Okay, then we can use the square root property to rewrite it as a square root of 9 times the square root of 3. So we don't say it, but this is a product of two roots. Okay. And then it will be square root of 9 is 3 times the square root of 3. Okay, so that what I mean by marching the square root, the perfect squares out the front door is you find the perfect square, and then you kind of just march it out in front, but you have to take the square root of it as you do it. Okay, but it's equivalent to going through this process with the product rule. Okay, so let's look at 24 with that in mind. I have the square root of 28. The square root of 28 is going to be 4 times 7. Okay. So the first perfect square I can think of is 4, and 4 divides 28, so I can rewrite 28 as 4 times 7. And then you can march this 4 out the front door, right? The square root of 4 is 2, so I'll have 2 root 7, 2 times root 7. And that's the idea. Let's look at one more, and then we'll throw some variables in the mix. So 28, we have the cube root of 54. So you're thinking perfect cubes that go into 54. So I don't think 8 goes in there. So 2 cubed is 8. And then 3 cubed is 27. I think 27 works, right? So we'll have the cube root of 27 times 2. And 27 is a perfect cube, so I can march them out the front door. So 3 times 3 times 3 is 27, right? So 3, and then times the cube root of 2, and that'll do it for that problem. Okay. Now with variables, what we're going to be thinking of is kind of a division. Okay, so you want to divide the exponents by the index of the root here. So let's take a look. Here we have the cube root of negative 32 x squared y cubed. Okay. So this is equal to, you can always pull negatives out of cube roots if you want. So let's just get that out of the way. So I have negative cube root of a perfect cube that goes into 32. And the first one you try is 8, and 8 definitely goes into it. So that's 8 times 4. And then we have x squared. And you're looking for exponents that are divisible by 3. Okay, so 2 is not divisible by 3, so you can't, it's not a perfect cube. But y cubed is. Okay? So we're going to be able to pull that out the front door by just dividing the exponent by 3. Okay, so in the end, we'll have, and if you don't see it, maybe I should take a step away from it for a second. I mean, why can't I pull? It's equivalent to what you're doing with like the cube root of 8 or the square root of 9. So for example, but down here, look, the square root of 9 is equal to the square root of 3 squared. Okay, so the exponent is divisible by 2, and you could pull it out the front door. So this would just be 3. The example, the cube root of 8. That's equivalent to taking the cube root of 2 cubed. Right? So in that case, you would be left with 2. If you had the cube root of, let's say, 24, that's equivalent to the cube root of, let's not make it 24, let's make it 16, okay? So that's equivalent to the cube root of 2 to the 4th, right? We can't bring out all powers of 2, though. We can only bring out the 2 cubed. So it would be 2 cubed times 2. And then you could bring out the 2 cubed, because this is the perfect cube right here. This is the 8. So it would remove the exponent, and you'd just be left with the cube root of 2. Okay, so what I'm trying to get to you is that the same phenomena is occurring here with these exponents. You're looking for exponents that are cubes, so this root will sort of cancel out the cube. Okay, so in this case, I can march the 8 out. That's a perfect cube. The y cubed is a perfect cube. So I'd end up with negative 2y, and then the cube root of 4x squared. Okay, let's try another one. 34. We have f of x equals the square root of 81 times x minus 2 squared. Okay. So 81 is definitely, it's 9 squared, so I could factor that out. And then this guy is also a perfect square. Okay. So I'd just end up with 9 times x minus 2. We want to be a little careful then with the x minus 2. It needs to be in absolute values. So remember, if you have the square root of something squared, that's equal to the absolute value of that something, right? The deal was that even if you had x being negative inside, or x is positive, so it's like 3 squared, that's going to be equal to the square root of 9, which is equal to 3. But that'll be the same deal with the square root of negative 3 squared. Okay, so that would be equal to the square root of 9, which is equal to 3. So you can't just say it's equal to negative 3. It's the absolute value of negative 3. Okay, so anyways, in general, we'll presume that we're not dealing with any of these issues where this could be negative. This thing could be negative, so we won't have to worry about the absolute values. So in section 3 here, we presume that we have non-negative quantities, and kick the whole idea of the absolute value under the rug. Okay, quantities. Right, so in general then, if you have the square root of something squared, we're not going to say it's absolute value of x anymore. We're going to say it's just plain old a. And in general, you could do that with any nth root power, nth root of a to the n. Now we'll just always say it's equal to a. Okay, so we don't have to deal with it. All right then, let's look at a bunch of these. So number 40, first off, we have the square root of x to the 5th. Okay. So we want exponents that are divisible by this index, and if it's not written, we assume it's a 2, right? So to get the perfect squares, you're looking for powers that are divisible by 2. So I can factor x to the 5th into x to the 4th times x to the 1. Okay? And then this guy is a perfect square. It's just x squared times x squared is x to the 4th. So you can divide 4 by 2 if you want to think of it that way, and you can pull that guy, kick him out the front door, and you get x squared times the square root of x. Let's get another. So 44. I have the square root of 40x cubed, and so that'll equal the square root of 4 times 10. So again, I want to march the perfect squares out front. And then x cubed, I need to factor that as well. So it would be x squared times x. Okay. So in this case, the perfect squares are right here and right here. And you can march those out the front door. So you'll end up with 2 times the square root. Oh, sorry, we're not done with that yet. My pens are all dying. Jeez. And I missed the trash can. That'll be a little bit of fun for me later, right? Pick up pens. I'm just looking for a nice pen that you can see, which would be great. I want to use some funky color. And of course I don't have any. Got a green one, so let's see how that goes. All right, so I can pull out the 2. I can pull out you know, the square root of x squared is just going to be x, and then the leftover is 10x, and that's it. Let's look at another. This will be apparently. I've forgotten which one I was working on. So this is 48. And we have the cube root of x cubed, y to the 17, z to the 2. Okay, so I'm looking for exponents that are divisible by 3. If they are, then they're perfect cubes and I can factor them out. Okay, so the first guy is a perfect cube. I don't need to do anything with that. This guy, though, is not. 17 is not divisible by 3. So I have to factor to an exponent that is. So y to the 15th, and then I'll have y squared, and then z squared is what it is. Okay. All right, so this will equal then, I can pull out the x cubed, so that'll be x. I can pull out the y to the 15th, that'll give me y to the 5th. You're just dividing the exponent by this number here. And then you're left over with the cube root of y squared, z squared. I got to get a different pen. This one is driving me crazy. Okay. Looking for something. Okay, so 56 now. Hopefully that looks a little better. Not really. We have the 5th root of 64x to the 7th times y to the 16th. Okay, we're playing the same game. I'm looking for now perfect fifths. And 64 sounds like it's some power of 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So 32 is a power, is 2 to the 5th. Okay, so 32, you can literally write 2 to the 5th if you'd rather. And then times 2, and then things that have exponents divisible by 5. So I need to go x to the 5th times x7, or sorry, times x2. And then y to the 15 times y to the 1. Okay, so I can kick this guy out, kick that guy out, kick that guy out, and you get 2x y cubed, and then times the 5th root of 2x squared y. Okay, so right, more simplification type problems, and these you kind of got to multiply them out and sort the perfect squares, multiply, then you simplify. So the deal will be you're given kind of a product where the individual roots are not simplifiable. They don't have any perfect squares in them. But if you're to multiply them out, then they have perfect squares, right? So if I gather a 3 from here and a 3 from here and multiply them together, you get 9, and that's a perfect square. So anyways, 3 times 6 is 18, and then 18 is the same as 9 times 2. And then this guy's a perfect square, so you can march them out front. So that'd be a 3 square root 2. So we got 66. We got the square root of 20x times the square root of 5x. And then what does that equal, right? So the square root of 20 times 5 is 100, and then x times x is x squared. So both of those now are perfect squares, and you can march them both out the front door. 10 times 10 is 100, so it's 10. X times x is x squared, so it just turns into 10x. Okay, one last one for this section. What do we got? 76. It's a cube root of 6x to the 7th y times the cube root of 9x to the 4th y to the 12th. Okay. So first multiply it out. Cube root of 54x to the 11th y to the 13th. And then start marching out the perfect cubes in this case. So 27 times 2 is 54. 27 is a perfect cube. And then times x to the 9, and then x to the 2, and then y to the 12 times y to the 1. So fill out the page there. Cube root, then you can march out your perfect cubes. There, and that guy. So it would be 3x cubed. So dividing this exponent by 3, and then 12 divided by 3 gives you y to the 4th, and then you're left with the cube root of 2x squared y. Okay, and that's it for this section.